Hi, thanks for joining me. Today I'm going to be showing you a constructive proof to the infinitude of prime numbers. Now before I get into it, you may have noticed that I have a little brace on my arm. I injured my arm the other day playing football, so hopefully I can still make some videos, but obviously my left arm will be out of action. Anyway, what we want to do is prove that there are infinitely many primes, and the way we're going to be doing that is showing that pi of n, so the number of primes less than or equal to some number n, we're going to show that that is bigger than or equal to log n over 2 log 2, and we're going to do this in a fairly intuitive / constructive way. Let's get stuck in. Okay, so we have that pi of n is the number of primes less than or equal to n, and we want to show that pi of n is bigger than or equal to log n over 2 log 2, and that will of course prove that there are infinitely many primes because this right hand side here is unbounded. So if you take n to infinity, this right hand side here goes to infinity, so this thing here must go to infinity, so the number of primes kind of less than or equal to infinity is infinite. Okay, and that will prove that there are infinitely many primes. So this is what we want to do. We want to prove this, and as I said, it's going to be a constructive proof. What we're going to do is consider any number t which is less than or equal to n. So n here is some arbitrary large positive integer, and we're going to consider some number t which is less than or equal to n. Now t has some prime factorization. Okay, we can write t out and write out the product of its primes, and then what we can do is essentially take out the biggest square number from that. So what I mean by that is we can write t in the form k squared times the first prime p1 to some power e1 times p2 to some power e2, and so on all the way up to the final prime, which is going to be pi of n to the en, like so. Okay, so any number t less than or equal to n can be written in this form here, where k is obviously going to be less than or equal to the square root of n, because if it was bigger than the square root of n, then t would be bigger than n, and then that would contradict that. So k must be less than or equal to the square root of n, but also these ei's are all either 0 or 1. Okay, so essentially we're taking t, we're taking out the biggest square number we can, and then anything that's left will either be 1, corresponding to prime to the power of 0, or it's going to be a particular prime number raised to the power of 1. Hence, we've got these ei's being either 0 or 1. Oh, this, sorry, shouldn't say n, it should say pi of n, like so. Okay, so this is essentially a way we can write any number less than or equal to n. But now let's just forget the t for a moment and just consider numbers of this form here that satisfy these two conditions here. How many such numbers are there? Well, for k, how many choices do we have? Well, by this condition here, we only have a square root of n choices for k. And well, how about for this e1? Remember the p1s, p2 and so on all the way up to p pi of n, they're fixed, but the ei's, well, they're either 0 or 1. So for e1 we have 2 choices, e2 we have 2 choices, and so on all the way down to e pi of n, for which we have 2 choices. So all in all, we have pi n 2's here. Okay, so of course this number here is square root of n times 2 to the power of pi of n, like so. But remember, this is simply the number of essentially the number of numbers we can write in this form here. But not all of them will be less than or equal to n. Because, for example, if you let k equal the square root of n, and then let each of the ei's be 1, then of course this number here is going to be bigger than n, so it won't correspond to a valid value of t. So essentially we've overcounted the number of t's there are. But we know how many t's there are less than or equal to n. There are precisely n of them. So this number here must be bigger than or equal to n for this all to make sense, because this left-hand side number here is the number of numbers in this form here, and we know that a subset of those numbers are the numbers which are less than or equal to n, and so we must have this guy here is bigger than or equal to n. And now all we're going to do is just work with this formula here, rearrange it, and we're going to get to this guy here. So let's just divide both sides by the square root of n first. So we get rid of this square root of n here, and this guy becomes a square root. Cool. Next we're going to take the log on both sides, so we get pi of n times log 2 is less than or also bigger than or equal to half log n. So I've used my log law there, that the log of square root of n is the same as a half log n, and then of course just dividing both sides by log 2 gives us that pi of n is bigger than or equal to log n all over 2 log 2. like so. Just squeeze it in there. And that's exactly what we wanted to prove. And as I said, this will prove that there are infinitely many primes. I hope you have enjoyed this video. It's not the standard proof to there being infinitely many primes, but it's a very constructive and very intuitive way of proving that there are infinitely many primes, and hopefully you haven't seen this one before. Anyway, thank you for watching. I'll catch you in the next one. Have a great day.